A central objective of chemical thermodynamics is predicting whether a process will occur spontaneously. We need to know if a reaction will proceed forward on its own, without a continuous input of external energy. This reaction coordinate graph models that spontaneity. This behavior is mathematically quantified by the change in Gibbs free energy, or delta G. A negative delta G indicates an exergonic process. The system releases energy, and the reaction spontaneously rolls downhill. A positive delta G is endergonic. The reaction requires a continuous energy input to ascend the gradient, making it non-spontaneous in the forward direction. At the absolute floor of the valley, the system can extract no further useful work. Here, delta G equals exactly 0, and the system is locked in a state of dynamic equilibrium. This equation isolates the physical drivers of that equilibrium. Gibbs free energy is defined as the change in enthalpy, delta H, minus the absolute temperature multiplied by the change in entropy, delta S. Determining whether any chemical reaction will happen requires deconstructing this formula. We must analyze the inherent physical tension between the potential energy stored in chemical bonds and the universal drive for energy to disperse. Enthalpy, represented by delta H, is the change in potential energy stored within chemical bonds and intermolecular forces at a constant pressure. It operates as a strict thermodynamic ledger. Breaking chemical bonds requires an energy input, resulting in an exothermic process with a positive delta H. Forming new bonds releases energy, yielding an exothermic process with a negative delta H. Enthalpy belongs to a category of properties known as state functions. This means its value is independent of the physical pathway taken. Whether a reaction occurs in 1 step or 10, the total enthalpy change depends only on the system's initial and final equilibrium states. This path independence is the basis of Hess's law. If we have a starting point, reactants A, and a single direct route to the endpoint, products D, the energy change for that route is fixed. If the reaction instead follows a convoluted series of intermediate steps to reach that exact same product, the total change in potential energy remains the same. This allows chemists to calculate the total enthalpy of complex reactions by simply summing the known standard heats of formation for each intermediate step. At the molecular level, the total enthalpy change of a reaction is the total energy absorbed to break the reactant bonds, minus the energy released, forming the product bonds. Enthalpy quantifies quantity energy ledger of a chemical system. But because endothermic reactions, those that absorb heat, still occur naturally, enthalpy alone cannot predict spontaneity. A common heuristic defines entropy as a measure of structural messiness or disorder. That definition is physically inaccurate. The rigorous thermodynamic definition of entropy, or delta S, is the strict measure of the spontaneous dispersal of energy at a specific temperature. The second law of thermodynamics states that energy in a closed system will always spontaneously spread out from a concentrated source to a wider area unless physically hindered. This side-by-side thermographic view reveals the physics of the impact. The spontaneous process is driven by the irreversible transfer and radiation of kinetic and thermal energy out into the surrounding environment. We see this principle in chemical phase changes. Transitioning from a highly ordered solid to a liquid or a liquid to a gas results in a massive increase in entropy. When a solid lattice breaks apart, the matter expands into a gas. The same amount of thermal energy is now forced to distribute over a vastly larger volume, dispersing across millions of newly available molecular microstates. Because the universe inherently drives toward this energetic dispersal, a positive entropy change acts as a physical driver for spontaneous reactions. We can now return to the full Gibbs free energy equation to analyze how the competing forces of enthalpy and entropy interact. Because temperature is measured in Kelvin, it operates as an absolute value and is always positive. This grid maps out the consequences. With temperature always positive, the final sign of delta G is dictated by the independent signs of enthalpy and entropy. In the first quadrant, a reaction releases energy, a negative delta H, and disperses energy, a positive delta S. This reaction is spontaneous at all possible temperatures. Conversely, if a reaction hoards energy and concentrates it, it is never spontaneous. The resulting delta G will remain positive regardless of temperature. In the remaining two quadrants, the signs of enthalpy and entropy match. In these cases, temperature determines which of the two variables dictates the final output. Consider the physical act of boiling water. Boiling requires absorbing heat, yielding a positive delta H, but it results in massive energy dispersal as liquid becomes steam, yielding a positive delta S. At room temperature, the enthalpy term mathematically outweighs the temperature times entropy. Delta G remains positive, and the water stays liquid. At exactly 373 Kelvin, the temperature multiplier makes the entropy term large enough to outweigh the positive enthalpy. Delta G becomes negative, and the phase change proceeds spontaneously. Crossing this thermal threshold dictates whether the dispersal of energy overcomes the enthalpy barrier, determining the spontaneous direction of the process. Predicting whether a reaction will happen is different from determining how fast it occurs. Spontaneity is not a measure of reaction speed. There is a physical separation between thermodynamics, measured by delta G, and kinetics, measured by activation energy, or EA. This coordinate graph charts that separation. A negative delta G guarantees a favorable reaction, but a steep activation energy barrier can prevent it for centuries. Catalysts accelerate reactions by providing a lower activation pathway. While they lower the peak, starting and ending enthalpy remain identical. The final link is the relationship between the standard Gibbs free energy and the chemical equilibrium constant, KEQ. As the standard free energy change becomes more negative, the equilibrium constant grows. This drives the reaction more aggressively toward the products. Gibbs free energy defines the final destination and equilibrium state of matter, regardless of the pathway or time required to reach it.